Okay, this is our first of three lessons that's going to walk us through powers and roots, primarily relevant, all three in their entirety for Math 053, which gets pretty deep into the weeds on this stuff. The beginning of this first one is also needed for Math 038 and Math 052, which have to do a basic amount of powers, exponents. And you can see there on the screen which specific sections those come up in. Quite a bit in Math 052, all over the place. And then the third lesson as well will be very similar. The first bit of that third lesson on roots will be relevant for Math 038 and 052. So in both those cases, for the exponents and the roots, 038 and 052 just have to do the basics, but Math 053 then gets quite a bit more involved. These lessons are all quite big. I'm going to try and move through fairly quickly, otherwise they'll be really long. On the other hand, I don't want to talk too fast either, so we'll try and strike a balance there if we can. Math 02 students, no powers, no roots in your courses, so I would recommend you just keep plugging away with what you're working on and ask any questions that you run into during our break time. Okay, so what is an exponent? So in math, you can imagine situations where you need to multiply a number by itself a whole bunch of times. So there we have some examples: 7 times 7, which of course is 49, 11 times 11, 121, 3 times 3 times 3 times 3. Now you're starting to think, oh, this is, I mean, at least you have a calculator, unless you're in the basic review unit of 052 or 053. So you can use your calculator. Still, it's starting to get a little annoying. 3 times 3 times 3 times 3. You might be able to save a little time because you could turn 3 times 3 into 9 and the other 3 times 3 into 9. And then 9 times 9 is 81. But now look at this: 2 times 2 times 2 times 2 times 2, and so on and so on. Type it all in, you'll get 512. The point we want to make here is simply that at some point, this is going to become really annoying to have to do this. And in fact, it might even get to the point of being near impossible, depending on how many times you are not multiplying that number by itself. So we came up with a shortcut. Instead of writing 7 times 7, we can write 7 to the power of 2 is how we would read that. Or even often we just say 7 to the 2. 11 times 11, we can write as 11 to the power of 2. And also we'll say squared as yet another little lazy thing when the number happens to be 2. 3 times 3 times 3 times 3, we can write as 3 to the power of 4. 2 to the power of 9, so that means 9 2's being multiplied by themselves. So that's all that an exponent means. So there we have another example. 5 to the power of 3 simply means 5 times 5 times 5. We also say 5 cubed when it is a 3. And we call that number down there, the 5 in this case, we call that the base. And the number of times we're going to multiply that number by itself is called the exponent, or the power. Unfortunately, one of those things that developed two different math words to describe it over the years. So exponent and power, we're talking the same thing. So the base is the number that you're multiplying over and over. The exponent is how many times you are going to multiply it. So here's a little chart. I'm just going to give you a minute to try this. So over here on the left, we have product form, 6 times 6 times 6. Over here on the right, I want you to put that into exponential form and vice versa. Okay, I think that's enough for this. Don't want to belabor it too much. So 6 times 6 times 6, that's 3 6's being multiplied. So we say 6 to the power of 3. 2 to the power of 7 means you're going to multiply 2 by itself 7 times. There we go. 2 times 2 times 2 times 2 times 2 times 2 times 2. That's 7 2's. There we have 5 y's being multiplied by themselves. So y to the power of 5. And how would we write p to the 4th? That would be p times p times p times p, like so. Okay. The most common mistake people make is they multiply. They look at this and they go 6 times 3 is 18. 2 times 7 is 14, but that is incorrect, as you can see. 6 times 6 times 6 is clearly not going to be 18, because 6 times 6 is already 36, and then times another 6, right? 2 times 2 times 2 times, that's not going to be 14, right? So remember, you don't multiply these two numbers. This tells you how many times you are going to multiply the base by itself. Luckily, you don't have to do this all by hand unless you're in chapter 1 or 2 of Math 052 or 053, in which case you don't have a calculator yet. However, they'll keep the numbers small, don't worry. If you are out of those review units, then you can pick up your calculator, and you want to look for, unfortunately, there's not consistency. It's usually one of those 4 buttons. Worst case, I have seen a calculator where you had to go into the menu to find the power button, which is a bit ridiculous. But I would say pretty well all scientific calculators will have one of those buttons or something similar. And here's how you use it. So if we want to evaluate 6 to the power of 3, or 6 cubed, we also say, then you type the 6, hit the power button, whichever one of those it is on your calculator, then the 3, then the equals button, and it should give you 216. This button here is just because that's what powers came to be represented on your computer with. It's the Shift 6 on your computer, which, by the way, if you're working on something like My Open Math, you'll be able to, if you need to type in a power, you can, I'm going to say I'm 99% sure you can use the Shift 6 and it'll automatically put the thing up in the power, or you can click on the little power option button that appears on your screen as well. This is called I'm going to say it wrong. I think it's called a parrot. Yes, I think so. So find whichever button it does and check to make sure you can match these answers. 8 to the power of 7, you type in 8, you hit the power button, type in 7, press equals, and you should get that really big number right there. Obviously much nicer than going 8 times 8 times 8 times 8 times 8 times 8 times 8 on your by hand. And this is just a little note of what I just said. Obviously, if you are in a chapter where you're not allowed a calculator yet, you don't have this luxury, but you soon will. All the more motivation to finish up those review chapters. When you have a fraction raised to a power, no big deal. We can simply raise the top and the bottom to the power separately. So 3/4 squared is actually 3 squared over 4 squared. And you can work each of those out. 3 squared is 3 times 3, which is 9. 4 squared is 4 times 4, which is 16. Over here, 2/5 to the power of 11. So we can just take the power into the top and the bottom separately. 2 to the 11 or 5 to the 11. Thank goodness for your calculator. Type those in and you will get that big ugly fraction right there. If they want it as a decimal, I suppose you could put it as a decimal, but generally we don't go to decimals unless the question wants us to, right? So the assumption is fraction answers unless we're told otherwise, always in the O5 courses. If the exponent is 1, then the thing is just equal to the base, and we usually don't bother to write that 1. So here's a little justification for that. Here we see some various powers of 5. Here we got 5 to the 6th, which is 6 5s being multiplied, 5 5s being multiplied, 4 5s being multiplied, 3, 2 5s being multiplied, 5 to the power of 2. So 5 to the power of 1 means there's just one 5. It's not actually being multiplied by anything, right? Because there's only one of it, so there's nothing to multiply by. So anything to the power of 1 is simply itself. 12 to the power of 1 is 12. 152 to the power of 1 is 152. B to the power of 1 is B, and we don't write that exponent in our answer. So if you get an answer that has an x to the power of 1 in it, for example, just write x. Don't write that power. You probably will get marked wrong on My Open Math, and if that's what you're using, and then I would add back some part marks for you. Okay, so for the Math 03 and 052 students, that's all you need to know about powers, what they are, how to evaluate them when they come up. So if you want to keep watching and take in the rest of this as a little preview, you are welcome to. If you want to sort of have it on in the background and get working on your practice questions, that's great too. So carrying on, exponent laws. So when you have more than one exponent in a single expression, there turn out to be some patterns that help us simplify. And there is different different courses and textbooks and teachers would list what they consider the exponent laws. This is what I consider to be everything that will be useful for you. And I'm going to suggest that you write those down on your resource sheet that you're allowed to have handwritten for your tests. We're going to do the 4 on the left in this lesson, and the 2 on the right we're going to save and do in the next lesson. So we're going to take a look at each of these individually, and we're first going to look very quickly at why they work, which you don't need to reproduce in any way on the test. You don't need to explain why they work. You just need to be able to use them. So we're going to justify why they're true, which helps you remember them, and then we're going to do a couple practice questions. So first one, b to the m times b to the n equals b to the m plus n. Or if we put that in words, when you multiply powers, here we're multiplying some powers that have the same base, they both have a base of b. That's important. If they don't have the same base, there is no rule. You can't do anything. When you multiply powers that have the same base, you add the exponents. Why would that be true? Well, let's look at a quick example just to justify this. If we want to multiply 7 squared times 7 cubed, we say to ourselves, well, what does 7 squared mean? That means 7 times 7. What does 7 cubed mean? That means 7 times 7 times 7. 3 sevens, right? Now look at that. We have 7 times 7 times 7 times 7 times 7. It came from a 7 squared and a 7 cubed, but really all it is now is 5 sevens being multiplied. 5 sevens being multiplied, that's just 7 to the 5th. And what we want to think is, where did that 5 come from? It came from going 2 plus 3, adding the exponents, not 2 times 3, right? So this confuses some at start because we're multiplying, right? You're multiplying, so it feels like you should multiply the exponents, but no, you're multiplying, you're not multiplying 2 times 3, you're multiplying 7 squared, which is 2 sevens, times 7 cubed, which is 3 sevens, making a total of 5 sevens being multiplied. So when you multiply, listen to the words, with the same base, you add the exponents. Let's look at a couple here. So that first one, we are multiplying. The bases are the same, right? Both of the bases are 3. So that means we will add the exponents. Now you can see already why this is useful, because if you were to type in 3 to the 15th and 3 to the 28th, you get massive, huge numbers. In fact, they'd be too big for your screen, and you would not be able to interpret them without first learning something called scientific notation that we're going to learn later on. You wouldn't even be able to get this answer with your calculator. But here we go. It's simply 3 to the power of 43. And now this did say do not evaluate, right? It just said simplify. So that means we don't need to try to turn that into a number. Thank goodness. 6 cubed times 6. Well, is this an exponent, this 6 right here? Well, actually, yes, it is. Because remember, 6 is just 6 to the power of 1. So we are multiplying 2 powers that have the same base. They both have a base of 6. That means we add the exponents, 3 plus 1. So 6 to the 3 times 6 to the 1 is 6 to the 3 plus 1, which is 6 to the 4. And here we have one with variables. That doesn't bother us at all. We're multiplying with the same base, so we add the exponents, 5 plus 7, v to the 12. All right, so there's rule number 1. When you multiply and the bases are the same, add the exponents. And I'm going to probably say a whole bunch of times, if the bases aren't the same, don't try to do anything, because you can't. Don't try and add anything or combine them in any way. If the bases aren't the same, if this was 3 to the 15th times 4 to the 28th, there's nothing you could do with it. All right, second rule. When you divide powers that have the same base, you subtract the exponents. This probably isn't too surprising given the first one, right? But let's look at why it's true really quickly. So let's think of something like 5 to the power of 6 divided by 5 to the power of 4. And the first thing we're going to remind ourselves is that division can always also be written as a fraction. So 5 to the 6 over 5 to the 4. Now, what is 5 to the power of 6? It's 5 times 5 times 5 times 5 times 5 times 5, 6 fives. 5 to the power of 4 is 4 fives being multiplied. And now we've done enough canceling so far that we can see that 4 of those 5s on the top will cancel out with the 4 on the bottom, and technically we'll leave a 1 behind on the bottom because each of these 5 over 5s reduce to 1 over 1, right? So we get 2 5s left on the top and simply a 1 left on the bottom, which of course dividing by 1 doesn't do anything. So this is 5 times 5, which is 5 squared. Well, where did that 2 come from? 6 minus 4, right? We had 6 5s on the top and 4 on the bottom. The 4 on the bottom canceled out 4 of the 1s on the top. So 6 minus 4 left 2 behind. And that's why this rule works. So here, let's try a few. Dividing, the bases are the same. I'm not going to pause right now in class, but if you are watching the video, you can always pause and try them and then see. So we're dividing. The bases are the same, so we subtract the exponents. 8 to the 21 divided by 8 to the 13 is equal to 8 to the power of 21 minus 13, which is 8 to the power of 8. 55 to the power of 19 divided by 55 to the power of 13. We are dividing, and the bases are the same, so we subtract the exponents, like so, 19 minus 13. And 19 minus 13 is 6. And the third one there, t to the power of 12 divided by t. It doesn't look like we're dividing two things that have exponents, but remember again that t can also be written as t to the power of 1. So we got t to the 12 divided by t to the 1. We're dividing with the same base, and so we subtract the exponents. 12 minus 1, t to the power of 11. Okay, so there's our first two rules. If you're multiplying and the bases are the same, you add the exponents. If you're dividing and the bases are the same, you subtract the exponents. Third law, when you raise a power to another power, you multiply the exponents. So here we got b to the m to the power of n, and we're claiming it's going to be b to the power of, remember this means m times n if we don't write anything in between two variables. So again, you don't need to know these justifications. I'm just showing you quickly why these rules work, right? What you need to be able to do is apply them. So let's think of something like 9 squared to the power of 3. What does that actually mean? Well, anything to the power of 3 means you take the thing and multiply itself by itself 3 times, right? So if the thing happens to be 9 squared, then you go 9 squared times 9 squared times 9 squared. That's 9 squared to the power of 3. But each of these 9 squareds actually means 9 times 9, like so. And those brackets aren't doing anything anymore, right? They were showing multiplication, but now it's just 9 times 9 times 9 times 9 times 9 times 9. Brackets no longer necessary. That is 6 9s being multiplied together, which we can write as 9 to the power of 6. So we see this time we did go 2 times 3, right? So when we raise a power to another power, and here again, this is just a justification. You don't need to reproduce this argument we made right here. We're just showing why these things do what they do. So when you raise a power to another power, then you multiply the exponents. So here's a couple to try. Maybe I will give you a minute this time. So 5 to the 7 to the power of 3. So we raise a power to another power. 7 times 3. So it's 5 to the power of 21. X to the 12 to the power of 4. It's a power raised to another power. 12 times 4, 48. Okay, and this is really just an overview. Like if we're doing one lesson here that covers all of a whole section or two, we're just overviewing the ideas, right? You really need to get in there and practice the questions in order to master this. Just watching this quick little run through isn't going to do it. So we now have 3 laws. And again, I would write all those laws on a single piece of paper. or screenshot. I'll put them back up in a second as well. Quickly, we're going to take a little sidebar here, and I just want to talk about instructions that you'll be given on questions, because students are often uncertain about the difference between a question that says simplify and a question that says evaluate. This is useful for everyone in all courses, by the way. So evaluate, if they use the word evaluate, they've given you a little extra piece of information. They have told you that you will be getting to a single numeric answer, like 5 or 127 or something, right? Or 2/3. 4.79. You'll be getting an actual number answer. So evaluate is actually just giving you a little tip, a little extra hint about what kind of answer you're going to get to. Simplify simply means that you want to make it as simple as you can by any means possible, reducing, combining, or including evaluating. So some people get confused. They think if it says simplify, they don't give a number answer. If it says simplify and you can get a number answer, then you do. If it says, but sometimes it'll say simplify and you can't actually get to a number answer, and that's why they said simplify, not evaluate. So these two things really mean the same thing, except evaluate is just telling you, by the way, you're going to get a number answer. Simplify means make it as simple as you can. You might not get a number answer, or you might. If you can, you do. So let's just look at a quick example of these instructions. So a question might say simplify, and it gives you this expression here. Let's do a little practice with the new rules that we've just been learning. Inside that bracket, we have a division, 3 to the 5 divided by 3 to the 3. We are dividing with the same base. So we subtract the exponents. 5 minus 3 is 2. Now, what do we got? We got a power raised to another power. That was the third law we did. We multiply the powers. That's 3 to the 2 times 4, which is 3 to the 8. And now, that's as simple as it gets without evaluating, but we can evaluate that, so we do, right? So just because it says simplify doesn't mean you don't evaluate if it's possible. Now, if you're thinking, how could you not evaluate? Let's take a look at the same exact question, but instead of a 3, there's a d. You can get all the way down to d to the 8th by following the exact same steps, but you don't know what d is, so you can't evaluate. So that's why it said simplify. They could not have said evaluate on this question, right? Because you can't evaluate because you don't know what d is. So again, you notice this is the exact same question, exact same instruction. You get as far as you can, and then if you can also get a number answer, then you do. If you can't, then of course you can't. The question could have also said evaluate, which would look exactly the same as the first one. And all that happened here is they told you, oh, by the way, you're going to be able to get an actual number answer. They just gave you a little tip, right? And I think I already said this. Yes, for the second question that had a variable, we could not have evaluated unless they tell us what d is. So if they said evaluate when d is 3, well, then yes, yeah, you can stick the 3 in and evaluate that. And then the last weird little instruction you will sometimes get, especially at the start of a unit, the one that we've been giving so far here in this lesson, is sometimes they will say simplify, but do not evaluate. That means you get down to 3 to the power of 8, but you don't actually turn it into a number. You won't run into that often on tests. That's usually at the very start of a unit when they want you to practice these steps here, but they don't really care about that last step there. They're like, yeah, you can all punch it into your calculator. Let's just practice this, right? Or maybe the evaluating just makes a giant mess and they're trying to save you the trouble, right? So there, hopefully that clears up the instructions you will see. And that's not just in exponents. You'll see that in all kinds of chapters in the course. Okay, so we got one more we're going to do right now, I think, or maybe two, I can't remember. So here we have two things multiplied and then raised to a power. And I claim that you can raise each of the two things separately to the power, like so. The words for that are a product raised to a power, that's this, a product, things multiplied, raised to a power, is the product of the powers. See, it's the two separate powers multiplied. And again, you do not need to know the next 30 seconds here as I show you why this works. What you need to know is simply how to use it, which we'll go through a few questions after. So 7 times 5 cubed, and again, this is just a demonstration. What does that really mean? That means 7 times 5 times itself 3 times. And again, those brackets aren't doing anything. This is just 7 times 5 times 7 times 5 times 7 times 5. Whoops. There we go. And I could reorganize those because I can multiply in any order. So that's 7 times 7 times 7 times 5 times 5 times 5. Well, wait a minute. That's just 7 cubed times 5 cubed, right? So again, this is not how you would do the question. This is just me showing you why the rule works, right? So we see that we had 7 times 5 cubed, but it turned out to be no different than 7 cubed times 5 cubed. So the product to a power is the product of the powers. Let's try a couple of these. We have, now these are the types of questions you'll actually have to do. We have 3xy all raised to the power of 2. So we know that this says 3 times x times y. We're just too lazy to write the times in there, right? So this is 3 things multiplied all raised to the 2. We can just take each of these things separately and raise them to the power of 2. So 3 squared times x squared times y squared. 3 squared, I know what that is. That's 9. But the other two I can't do anything with, so there's my final answer, 9x squared y squared. Here we have a whole bunch of things multiplied and raised to the power of 4. We can just take each of them separately. 2 to the 4 times r to the 5th to the 4 times s cubed to the 4 times t to the 7th to the 4. I'll let you stare at that for a second. I just took all those 4 things being multiplied and raised each of them separately to the power of 4. Okay, let's work these out one at a time. 2 to the power of 4 means 2 times 2 times 2 times 2. Or use your calculator and your power button. Either way, you should get 16 for that. R to the 5th to the power of 4, when we raise a power to a power, we multiply the exponents. R to the 20. S cubed to the power of 4. Again, we're raising a power to a power, so we multiply the exponents. 3 times 4 is 12. And t to the 7 to the 4, raising a power to a power, so we multiply the exponents. And there is our final answer for that question. So again, I'm just going to repeat one more time just to be sure. Those justifications for why these worked, don't try and do them though, these questions that way. That was just showing you why the rules work, right? And then the questions we did afterwards for each of those are the types of questions you have to do. Now, we want to stress this for this last rule, that is only for multiplication. It does not work for addition or subtraction. So a times b to a power is a to the power times b to the power. Kind of think of it as the power going through the bracket. But these are both not true. A plus b to a power, you can't go a to the m plus b to the m. It is false. Wrong, wrong, wrong. Same with a minus b to a power, you can't just subtract the powers. You can try that with some numbers if you want, and you'll see why they don't work. This right here, what you are looking at on that screen, is the number one most persistent error that continues to happen. I've taught all levels of high school math. I've taught university level calculus. I've tutored and helped students in university math, and they still They know it. They know this is true, that you can't do these two things, and they still do it over and over and over. And you point it out and they say, oh, yeah, of course, I knew that. So try and lock this one in your head. You cannot run a power through a bracket with addition or subtraction. Only like this with multiplication, or we'll see later with division as well. Okay, so there is our laws again that we put up earlier. We've done the 4 on the left. And we're going to save those two for the next lesson. And if you are good at taking screenshots, then you can screenshot that if you'd like. I'm going to take one right now, and I can email that to anyone who would like it, because those you want to write on your resource sheet and have them with you for the test. And again, I'll say we got one more time. As I went through and showed you why they work, you never need to do that. You just need to know how to use them, as we looked at in the examples after each one. Okay, we got one more little thing to talk about before we move on, or before we finish up here. So we're going to, multiplying monomials sounds way more complicated than it is. A monomial simply is an expression that is all multiplying and dividing, no adding and subtracting. And when we multiply monomials, we just multiply all the corresponding pieces. So there's a couple examples of monomials. Take a look at this, all multiplication. 3 times x to the 5th times y squared. No adding, no subtracting. 8 times x to the 7th times y to the 4th, all multiplying, no adding or subtracting. If there is adding or subtracting in there, then doing the multiplication gets way harder, but if there's all multiplying, it's quite easy. So let's multiply those two. 3x to the 5th y squared times 8x to the 7th y to the 4th. All multiplying in the first, all multiplying in the second. So we can simply take the corresponding pairs and multiply them together. So what I mean by that is the 3 and the 8 are numbers, so we can multiply those. We can take the x to the 5th and x to the 7th and multiply those. And the y squared and y to the 4th and multiply those, like so. The reason for that probably is clear, because remember when it's this times this times this times this times this times this, right? The brackets don't actually mean anything. It's all multiplying, and we can put things in any order we want when we're multiplying a whole bunch of things. So 3 times 8 is 24. X to the 5th times x to the 7th, we are multiplying with the same base. So we add the exponents. 5 plus 7 is 12. Y squared times y to the 4th, we're multiplying with the same base. So we add the exponents, right? So not 5 times 7, 5 plus 7. But out here at front, this is just 3 times 8. So you multiply 24, right? But this is x to the 5 times x to the 7, multiplying exponents that have the same base, add the exponents. And then we wouldn't write it with all those brackets that are unnecessary. We would just write 24x to the 12th, y to the 6th. And probably many of you see I could have skipped both these middle two steps, just gone 3 times 8 is 24. X to the 5th times x to the 7 is x to the 12th. Y squared times y to the 4, y to the 6th, right? Just jump right to my answer. There's one for you to try. Okay, let's take a look. So we got all multiplication and all multiplication. So we know we can do that multiplication in any order. We're going to multiply the numbers together and then the corresponding powers of m and n together. And notice what I did here. I spotted that n there, which I rewrote as n to the power of 1, because it's very common mistake on this for people to have as their answer just n to the 17, because they don't see any power here, and so they don't add anything. But remember, a variable by itself is actually n to the power of 1. We're just too lazy to write that 1 there. So negative 2 times 15 is negative 30. N cubed times m to the 4th, 3 plus 4 is 7. N to the 17 times n to the 1, 17 plus 1 is 18. And there is our answer.